There we go. We're going.
All righty. All right, friends. So, home stretch time in Calc 2. Things get different. Yeah, and so the exams, they were pretty good. I don't think anybody should be upset with how they turned out. You might not be super stoked, but nothing to be upset about, you know? Not like stoked like Olivia was for that whiteboard.
I really like whiteboards.
That makes me happy. So, yeah, things really switch up in our class now. So kind of a whole different vibe. We're not even going to see integrals for a while. So that'll be refreshing. Woo, yeah, we will again. We're going to use them to do stuff with new ideas that we're going to be talking about. But let's get rolling. So first off, there's a new web work that will be opening up. And this one is currently due Sunday night. You know, midnight, something like that, midnight hour. And, you know, if we need to extend that, we will too. But let's shoot for that right now, then maybe start on it by Friday. We'll probably take some time in class on Friday to work on it, so that's what I'm thinking. Tentatively do Sunday night. You know how you can manipulate me though. I'm easy. All right, so we are starting, like I said, the last part of this class, which is kind of my favorite part of this class. We're going to start talking about sequences and series. We're going to spend about half a week on sequences, couple classes, and then the rest of the semester is going to be on series, and this could also be called infinite series. So lots of strangeness afoot. Let's start with sequences today. So a sequence, this is real easy. I'm going to give you a couple ways to think about sequences. So a sequence is a list of numbers. That's like true, and it's probably the most intuitive way to think about them. And the sequence, a list of numbers can be finite. So we have, for example, a list where I say, oh, I've got a finite list, it's 1, 3, 5, 7. And then you start to get the rhythm. A lot of this whole part is rhythms. Can I catch the pattern in the numbers? And we did some of this, Danielle, but we're going to do it way, way deeper than we did in discrete. And we're going to add some calculus elements to it. And maybe I take this up to some place, like right now it looks like it just keeps on cruising, but I could end it somewhere at you know, any odd number, I guess, really. Why don't you pick your favorite odd number and tack it at the end there? Because that's what I'm trying to indicate here, that we are doing the odd numbers. Let me give this to Ms. Vivian before I forget. So finite list, it terminates. What we will spend most of our time on are infinite sequences. And an infinite sequence keeps on going like this. Now Daniela, you can't participate in some of these because some of my examples are kind of going to be the same. You've already seen what's up with that. Here's an infinite sequence of numbers. Does anybody recognize this? Oh, does anybody but one person recognize this?
Fibonacci.
Fibonacci, nice. This is a Fibonacci sequence right here. The way you get the next number in the sequence is you add the previous two. So notice 2 is 1 plus 1, 3 is 1 plus 2, etc. So the next number here would be what?
34.
34. Exactly. Then we can keep on cruising. So this sequence is famous and infamous, and I need different classes because there's just, I just saw 2 Cassies. So nothing wrong, that, you know.
No, that'd be horrible.
That would be cool. Yeah, you said one Cassie goes and does this stuff, other Cassie That's fun.
That's on it.
Yeah. Yeah, I don't know where I was going with that. Oh yeah, infamous sequence. There's like a book, the Da Vinci Code. You ever seen this? And there's like all sorts of stuff in there about this code, about this sequence, and there's lore in math and science about how the petals on a flower are always, the number of petals on a flower are always one of these. This actually came about because Fibonacci was studying rabbit populations and like how they multiply and then like the rabbits are hooking up and making more rabbits, and you can go read about that, like how he got this sequence. But it was from a study of a natural process. So people extrapolated it to all sorts of things. If you take a look at the ratios of these numbers, so let's see here, so 1 to 1, 2 to 1, 3 to 2, 5 to 3, 8 to 5, and you start cranking out these numbers in this. So here's a new sequence. Can you see the pattern and know what the next one is? What's the next one? 13 over 8, yeah. So I'm just grabbing pairs of these and putting the larger one on top. This sequence actually gets closer and closer. If you crank out these values, it gets closer and closer to, so approaches what's called phi, which is the golden ratio. And the golden ratio is used in Greek art all over the place. It's supposed to be one of the most appealing ratios. And it's like 1.513, I think it was on. So it's the golden ratio. There's like also a silver ratio and a copper ratio and all this kind of stuff. But if you have a rectangle and the ratio of the longer side, L to the shorter side H, so if L over H is equal to phi, that's supposed to be that is a golden rectangle. And theoretically, that's the most appealing to our human eye. Your mileage may vary. There's been studies done where they like took people and they gave them a bunch of rectangles and they did statistical analysis, and it seemed that most people appealed, the golden rectangle was the most appealing. So these sequences, we're gonna have lots of fun with them. We're gonna get a nice pen, not this pen. There we go. Let's look at some sequences. Oh, thanks. Sorry about that. Actually, let's get back. Thanks. This is good. Yeah, you just give me that thing. I'm throwing that away. I keep putting the same bad pens back in my bag, and then every time I come in here and randomly grabbing them. So there's probably ones from the first of the semester where I was like, bad pen, still in there, still in the damn bag. So before we look at more sequences, let's think of another way to talk about them. A sequence, so this is an alternate definition. A sequence is a function. Sometimes books will give people this definition first, and this is like the worst thing to tell people first, because it's just really abstract. And what I mean is a function from the natural numbers, so n, and this is 1, 2, 3, on up, it's the positive integers, to r, which is the real numbers. So thinking about it like that is kind of like, I don't know how helpful that is. But it does help in thinking of it as a picture. So a sequence can be thought of as a picture of a bunch of points. So right here, let's say here I've got n, these are the natural numbers, here's 1, 2, 3, 4, on up. And then here's the real numbers. And well, let's look at that sequence over there. So that Fibonacci sequence, so that goes something like this, 1. So there's my first number, it's 1. My second number is 1. My third number is 2. So that's 2, so I'm plotting that. Fourth number is 3, etc. So you can make a nice plot. And I love doing this because it really helps you to understand patterns. So graphs of sequences are super useful. I'm just gonna write that actually. It's super useful for detecting patterns. Sequences like this is science. If you're a scientist taking observations of a natural phenomena, this is the observation number, this is the measurement right here. So it's not an abstracted thing at all. It's something that scientists use all the time. A lot of times for a scientist, this would be like the time axis here at different time intervals, taking measurements at different times. So that's the two main ways to talk about it. To write a general sequence, and this is going to be where things start to get a little more abstracted. To write a general sequence, we use the following notation. So I would say my first term is a sub 1, a sub 2 is the second, a sub 3, a sub 4. So I've got a list of numbers separated by commas. And then I would put comma, dot, dot, dot. If I pick this up a little later, it's finite. If I like just said up to A100, that's a finite sequence. But for us, mostly we're going to deal with infinite sequences and just use ellipses to indicate ad infinitum, etc. forever. So this is just the list. We would write it in compact form, so compactly as, there's a couple ways to do this. Use parentheses. Inside here, put a sub n. And sometimes this can be a formula. Depending on n. Or just the letter. Just the letter with a subscript. Like you see here. On the outside, kind of like we do with integrals, where we put a lower limit and an upper limit, you can put down here where you want n to start. So if you put n equals 3 down here, and you maybe put an infinity up here, this sequence basically is just the following list. It's a sub 3, a sub 4, a sub 5. So this is my starting index. And this would be my terminal index, where I wanted it to end. I guess I should tell you, this number down here is called the index. The A's themselves, each one of these is a term in the sequence. So these are the terms of the sequence. And then I probably should close that off. So that's one way. I might slip once in a while and write something like this, or occasionally. I don't know. It seems like too many. There's too many of some letter in there. But who gives a shit? You know what I mean. Or occasionally you would just write a sub n like this. N equals start to end. And quite often, if it doesn't matter, if we don't care where it starts, and that's going to be the case a lot, we're mostly concerned with end behavior in these things, so we might just write, or no indices at all, no indice range at all, sorry, index range at all, and I just write like this. And you just know it's a sequence, and you assume it's an infinite sequence, and it doesn't matter if it starts at 10 or 3 or 1. Alrighty, so now let's have some fun. Let's have some fun. One of your tasks in the web work and in this class is discerning patterns and then expressing them mathematically. That's the fun part, right? We get to like figure out what is the rhythm here and how do I communicate that to another person who I can assume understands some math. So let's just look at some examples. And then I'll give you some useful formulas along the way and so forth and etc. So, let's start here. What's the next number in the sequence? 7 over 16. Yeah, and then what would be the next? 7 over 32, right? So you're doubling, the top is staying the same, the bottom is doubling every single time. Let's say we wanted to come up with a formula for this. So, is everybody cool on grabbing the rhythm, like knowing what comes next? And we're gonna get a little more tricky as we get through here, right? We're warming up. We just got the tiny little weights out right now. So let's get a formula. This is where it becomes challenging. In other words, what do I mean by that? So I want to write this as a sequence. I want a sub n in terms of a function of n. So this is the formula that we want. And I want a sub 1 to be 7. I want a sub 2 to be 7 halves. A sub 3 to be 7 fourths. On down the line. I want the formula for this. So a sub n equals, so that if someone said to me, what's the 3001st term in this sequence, I could compute it without having to let go. All right, there's 3. I've only got 2,998 more to go, right? We just want to crank it out. What's going on in the bottom here? It's doubling every time, yeah. Is there a nice way to write, let's see, we could put this one, so maybe I'd even write that like that, I'm looking for a pattern. Because these are all fractions, I might as well write that first one as a fraction. So Vivian said, yeah, they're doubling each time. Is there any one formula I could use to write those bottom ones out? So what power of 2 is that? 2 to the 0, yeah, exactly. 2 to the first, 2 squared. So here I'm catching the fact that these are powers of 2. And that gets what Vivian said, they're going to double each time we go up, each time the index goes up. So, what's the formula for a sub n going to look like?
7 over 2 to the power of n minus 1.
Beautiful. Nice. Notice how the power on the 2 is 1 less than the index. So that's why Kitcher suggested subtracting 1 from it. Is this making sense? You good with this? All right, nice. So we've got this, and then you would probably, maybe just, if we wanted to be super precise and let everybody know this actually started at 7, we would give this index right here. Cool. All right, good warm up. Let's talk about a few things that are helpful, will be absolutely helpful. I'm working through this stuff. Let's see, what did I have next? That's not even my notes. These is my notes. Here's a good one. Let me give you some helpful helpful sequence things. I don't even know what to call them. I thought I would figure it out by now. -1 to the n. Oh man, is that helpful. This allows us to alternate back and forth. So if you think about this, when n equals 1, we've got -1. When n equals 2, we've got +1, and then we just keep alternating. So we get this lovely alternation like that. What would happen, what if I wanted to start at 1? What if I wanted this sequence here instead? What could I do?
N plus or minus 1.
Yeah, just add 1, kick in an extra power on top, or take this and you could go, oh, notice how that's the same thing as that. Just negate everything. Lots of ways to write things. You're gonna find that things aren't unique with this. There's gonna be lots of, I don't know if creative expression is exactly the way, but kind of, right? Get a little nutty with this. So be aware that changing the exponent on this changes the parity, the way that ones and minus ones fall. So that's a good one. Ooh, that's a fancy N. That really got fancy. What is that?
Factorial.
Factorial, yeah, absolutely. So this is N factorial. What is that, Lou?
1 times 2 times 3 times 4. Like it's like.
Beautiful, beautiful. So this is equal to the product of all numbers between 1 and n. And so 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. Hey, check this out. 4 factorial is actually 4 times 3 factorial. Does that make sense? No? So you can get the next factorial by multiplying the previous one by the next number. So what's 5 factorial? 5 times 4 factorial. Just noting that, because that's actually going to matter to us in about a week or so. And then this is just 24, and then this is 120, and these blow up super fast, really steep sequence. And I'll show you a graph in a bit here. And I've got some graphing apps that'll help us and help you when you're thinking about these things. So, whoa, what's 1. It's defined to be 1. It's weird. I can prove to you that it's 1, but we have to talk about this thing called the gamma function, and we don't want to do that because I said we wouldn't talk about integrals. And the gamma function needs integrals. So factorial is a shadow of the gamma function. Just I don't know why I made it plural. Yeah. Cool looking symbol, nice capital gamma. Awesome, awesome function. But not what we're concerned about. We just need to know that. Let's see, what are some other little helpful things that I thought you might want to talk about? That's probably about it, I think, in terms of little tricks that'll help. Okay, so here's the next sequence. 1, 3, 1, 3, 1, 3, 1, 3. I think you got the rhythm. I hope so. I hope you don't think 5 is next or something weird like that. Pi next. No, it's 1, 3 forever. Could you come up with a formula? Take a minute. So here's A1, here's A2. Lots of we're gonna just have so many puzzles. It's puzzles, right? It's a fun little game. And there are multiple right answers here. I think. Okay. You could use your whiteboard. You think you got them? Yeah, yeah. So the n shouldn't go on, because right now the n is acting on the 1. I would just put it outside the parentheses.
Mine
Okay.
is right.
Yeah, let's see, when is that? So you're gonna, yeah, yes. think about that, those alternating, see how that bounces.
Oh.
That can help, that's gonna be the key. So if you're having trouble like figuring it out, when you see things bouncing, incorporate a -1 to the end or something like that. That can really help you with this. I'm gonna plot it out. So let's see. So, just let me know if you got this. So notice how, if you take 2 as your base, kind of like your anchor, it's 2 minus 1, 2 plus 1, 2 minus 1, 2 plus 1. So that's how you can incorporate the alternation here. So we could just say a sub n is 2 plus, and then I write this out, and then I test it, because sometimes you have to tweak this to make sure it's getting the +1 and the -1 in the right order. But I think we're good here, because a sub 1, so notice that a sub 1 would be 2 plus -1 to the first. That checks out, that's 1. A sub 2 is equal to 2 plus -1 squared. 2 plus 1 is 3, and then I'm good to go. And let's put a little n equals 1, 2, 3. Is there any questions, or like, how many folks got that? I'm curious. 701. 1. Cool. Did you get that one, Danielle? No. Okay. That's all good. We're just warming up. You're going to get used to more and more of this. Oh, here's one. Let's keep practicing this right here. So here's a sequence. So this is A1, A2, 3, and it's giving you a nice little hint there. Can you come up with a formula for A sub n? Like, see, I secretly made you go to math club. This is math club stuff. We do see if there's a -1 to the end in here, right? Because we got that plus minus going on, so you definitely know there's some form of that going on in there. Do I need to adjust that exponent on there? I do, right? Because I want to start at +1. When n is 1, I want a +1. So you can put a -1, you can put a +1, all good. Just to set that first one as a 1 and then get the -1 after that. Does that make sense what I'm saying there? When I talk about tweaking that exponent? Olivia, are you cool with that? Okay, yeah. And anybody need to talk about that? Good. Okay, then what's happening? So if I didn't have plus and minuses here, what would be the formula? A sub n would be what? So if I didn't have the alternation, that would be the formula. And I'd like put these two things together. Yeah, so now just multiply by n, and we're good to go. So it's a combo. It's gonna be a sub 2 is -1 cubed, that gives me a negative, and then times 3. So check out how this formula is working. So a sub 1 is -1 squared times 1, that's 1. Then you check, you make a stab at it, and then you test to see if your hypothesis was right. And it's looking like a go. Let's try one more. Oh, we'll try so many more. Don't worry. This won't be the last one. So let's see. Maybe some sequence friends of ours had a baby, and they made this. So you've got two things, right? You've got a top rhythm and a bottom rhythm. Handle those as separate problems. Figure out the top, figure out the bottom. They don't seem to be intertwined. So, yes. Yeah. Oh. Interesting. No, because when n gets really big, it's going to be so big that you can't get a negative out of it, right? So like when n is 10, I've got 9 minus 1. Then when n is 11, I've got 10 plus 1. So I lose the minus plus,
Oh,
you
okay,
see?
okay,
Yeah,
yeah.
this is, so your sequence here starts off as 0. So yours starts off at 1, I like that. And it might work for maybe the first couple, I think that's
But then
yeah.
after that-
After that, it doesn't work. So
Okay,
yeah,
cool.
yeah. Yes, sir. Beauty. Absolutely. You do, Carly. Sorry, I don't want no pressure. How's it going over here, David? Good here.
This is wrong.
That is right.
It's right.
That is right. Shouldn't be your first thought of yourself. That's right.
I'm not good at this stuff. But I'm gonna get good.
You are gonna get really freaking good at it. That's looking good, Vivian. Yeah, you're getting the right rhythm. You're just testing out your, yeah, that looks beautiful. Yeah. Cassie, how's it going? I don't know about the bottom, so because it's just off by a little bit, but that's the right idea. Danielle, you feel good? Yeah. Ooh, how's it going here? Yeah, and then your top is gonna be that. That's your top. So put them in together as one, because so that is those two at the same time. Yeah, but they're each quite right. So the top is this thing, right? Here's my top formula right here. So it's 2 plus minus 1 to the n. If we start at n equals 1. And then the bottom is powers of 2. So it's actually just 2 to the n down there, because when n is 1, I get 2 to the first. When n is 2, I get 2 squared on up. Any questions on that one? Is it looking good, Carly? Yeah. Awesome. Let's see, what time is it? How much more fun can we have? Well, infinite amounts. Yeah, I think I have to. Let's do one more. I think this is worthwhile. I think this is worth our time. If you could do, just going forward is easy. If I give you the formula, you own the sequence, right? So if I told you, A sub n is the sine of n, you might not like that. That might hurt a little bit. But if I told you this, you could crank out all the values. So that's easy. Get the formula and get the sequence. Once you got that, you got it. The thing we're doing is the tricky part. So let's do one more. Here's A sub 1. Here's A sub 2. Let's A sub n. Get my little app fired up here. Are you excited? Nerd jokes. I hope we're all excited about factorials, right? This is 1 over 1. This is 1 over 1 times 2. 1 times 2 times 3. 1 times 2 times 3 times 4. So A sub n is just 1 over n factorial. Nice formula. And if you remembered the factorial, you caught that. If not, it might have been a little painful. Otherwise, trying to express it. But you could, like, let's say you didn't know that. I mean, you could literally do this. You didn't know that notation. You could just go write it out like that as a product and express yourself in the only way, maybe the only language you had. You didn't have this word. So I put this app, there's a link to it in World Class in the new announcement. Really nice little sequence app, just very simple. Doesn't require anything fancy. There's no sliders, there's no options. It's like enter the freaking formula. So for example, sine of n over n squared, that thing that I put up there just seconds ago, and hit enter, and voila. I don't know if you can zoom. I don't think so. It's so basic, there's just very little to do here. But one of the things I want you to notice is the end behavior. So this is the sequence I'm looking at. Where did my pen go? So we're now looking at a much more complicated, in some ways, sequence. We've got the sequence. Notice how I'm going to write it without even notating it as an A sub whatever. So this is a sequence, and it's, when you look at this, you can extrapolate that the sequence looks like this: sine of 1 over 1 squared, sine of 2 over 2 squared. And these numbers, I don't know what sine of 1 and 2 are. These aren't like multiples of pi, so they're weird. So an app like this, or Excel is fantastic for cranking out things like this. But what you do see is an alternation in sign, SIGN, because of the alternation in sign, SINE. So see how this thing bounces? What does it look like its long-term behavior is? If I went way out, what is it approaching?
0.
0. Awesome. So the thing you just did was you took a limit in your head. You're doing an analysis that's saying that the sine of n over n squared approaches 0 as n gets bigger and bigger. You can do that with that graph, right? Like it might not be obvious here. In fact, it could be kind of weird looking at this, trying to figure out what the hell is this thing doing. Doesn't matter that this is crazy stuff. For us, the big concern is what happens eventually for these sequences. What is the long-term behavior? Let's pop a couple others out there. Let's see here. Let me show you some stuff. I think that this will encourage you, but what you actually know, because you actually know much more than probably thinking. Actually, let me put that 4n on top there. 4n there, so that's quantity 2 plus 4n over 3 plus n. So let me write out the sequence I just put in there. Let's see if we can maybe discern what's going to happen before I even hit enter. So it was 2 plus 4n. So a sub n is 2 plus 4n over, now what did I say in the bottom? 3 plus n. Okay. So we can let's grab the first couple. Anytime you get a sequence, start plugging stuff in just to see, just to get a handle for it. Because this is one of the few things in math that we can really, hold quite well. So it's going to be 2 plus 4 over 3 plus 1, so is that 6/4? You can simplify if you wanted. A sub 2 is going to be, notice how I'm adding another 4 each time, so it's going to be 10. And on the bottom, I'm just adding 1, 10/5. Is this looking okay? And let me know. And then a sub 3, what's a sub 3 going to be? 14/6, beautiful. And then we got the rhythm, right? And we don't even need to look back at the formula. We're just starting to catch what's changing between subsequent terms. What do you think happens long term on this? So this is 3.5, this is 1.5, this is 2, this is like more than 2, but not 3. Where do you think we're going?
Infinity?
N is going to go to infinity, but will the value, so you're suggesting that the output blows up, Blue? That is not true. That's okay, that's a good guess. What happens when n is really big? So let's say n is a million. Can I even write a million? There's n is a million. So what does a sub a million look like? It's going to be 2 plus 4 million. Is that right? Yeah. Over 3 plus 1 million.
Closer to 4?
It seems like it's getting closer to 4. Notice this 2 and this 3 don't matter, right? And if I add more zeros here, this is all that happens. This 2 and this 3 matter less and less when n is really big. And so I think what Kitra did was go, oh, this is roughly 4. Yeah. So remember L'Hopital's rule and all that stuff? And no. I'm very tired, no. But I know you do, kind of. So if I wanted to take this sequence and understand it, if I asked you, what is the limit as n goes to infinity of a sub n, you would look at this thing and go, it's really the same thing as if there were an x here and I was asking you for the limit as x goes to infinity. You can think of it the exact same way. So this is going to be limit as n goes to infinity. I'm just going to write this out, 2 plus 4n, and 3 plus n. Thinking of it this way, can you see that 4 is the thing we approach? Because it's going to be 4 times a big ass number over the big ass number. So we can see it's going to be 4, but I can also realize where's the top going. So now, Lou, the top itself is going to infinity. If I just had the top, if I just had the bottom, this is the form, infinity over infinity. So I can L'Hopital that. So it's an indeterminate form, so by L'Hopital's rule, limit as n goes to infinity, what's the derivative of the top with respect to n? 4. What's the derivative of the bottom with respect to n?
N.
Nope. 1.
1.
Yes. That's it.
There's only one of them.
It was one of those, absolutely. Because this is like, what's the derivative of x with respect to x if you want? So we just got a different letter here. So the answer here, now I don't even have variables, right? This is a constant thing, so the answer is 4. So all the calc that you know or can review, refresh up on, is going to apply here. So L'Hopital's rule is like one of those things that really helps. But what helps the most is having a picture and really understanding the sequence. So like having these visuals for me is like key. Because for this one here, it's just pretty unpleasant to figure out. There's some tricks we'd have to look at. So let's look at a few little rules. Actually, let's talk more about what does it mean to say, let's just talk about long-term behavior. Long-term behavior of a sequence. And we'll just call it A sub n. Draw you a picture. And I'm going to make this value L on this axis. So this is going to be my terms here. And you could just put A sub n, and then this is your n down here. And we've got 1, 2, 3. Put a dot, dot, dot if you're keeping notes, and pick this up a little later. So maybe even a little dot, dot, dot in there. Show that this is much later out there. So something happens. This is the mysterious region where time just jumps forward. So my sequence, A sub n, if it gets closer and closer to a value, L, as I move out this way, and it doesn't have to be in any particular regular way. But notice how here, as n gets larger, A sub n gets closer to value L. Now I'm gonna do something I never do, and I'm gonna like show you the official calculus definition. So we're just gonna do it. We're just gonna deal with it emotionally. It's gonna be okay. This means, and I'm gonna write this out, that the limit as n goes to infinity of A sub n equals L. The sequence settles down toward this value. But more importantly, I can get as close to L as I want by moving out far enough. So technically, this is the thing I never do. Given any tolerance epsilon, which is a positive number. So this is just a positive number. And it's usually a small positive number. We can find a cutoff, capital N, and I'll draw a picture for this in just a second, so that the A sub n's are within epsilon of L, so that's L minus epsilon, L plus epsilon, and they live in that range no matter how small epsilon is when the index n is bigger than or equal to that cutoff. I'm going to kill my finger here because I'm going to draw you another picture, because I do want you to understand this. Stop. Come back to this. I've got maybe a really awesome story to tell you either today or like one of my favorite math stories to tell. I don't think it's going to happen today. Right. Let's start today. So what does this mean? This means this whole gets closer thing, gets larger. This took people a long time to figure out, mathematicians a long time to figure out. So to say this means you tell me how close you want to get to L. And so you say, hey, can you get all the terms to live within L plus epsilon and L minus epsilon? In other words, if I make a little tube, and I like to call these epsilon tubes. If I make a little tube like that, can you find me a place in the future, down the line, and that is that capital N, can you find me a capital N where the sequence lives in this tube from there on out? And then before that, it might not at all. It might be outside of it. So what it means to be the limit, what it means to say the limit is L is no matter how tiny you make this tube, I can always find a cutoff where the sequence lives in that tube from that point on. So that's technically what this means. And I'm going to write it out for the mathematicians in the audience here. So here's the fun part. I'm going to get this. I never freaking do this in here. Super mathtastically, for all epsilon greater than 0, because this is just so beautiful. I think I told you I wanted to be a wizard, right? And then I became a mathematician instead because I can write things like this. For every positive epsilon, there exists an n, which is a natural number. Oh, let's look at that. For all epsilon, there is some n in the natural numbers, such that, there's even a weird little symbol for that, but I won't get too crazy, such that a sub n minus L in absolute value is less than epsilon. That's just this written in a fancy way. When n is greater than or equal to n. That is the beauty. For the math majors in here, when you take real analysis, welcome to real analysis. This is what, oh yeah. For the rest of you, don't look at it if you don't like it. It'll all be good. That gets my blood boiling. Gets me stirred up. Okay, so that's what a limit is. You don't have to, we don't even have to talk about that. We don't need to talk about that again. Let's talk about some results here. Limit theorem. These you do need. Limit theorems. And these are just helpful for finding limits. Notice how I slowly brought us back to limits, the thing that everybody is like about without like really telling you we were going to do that. I didn't want you to get scared. It's like when you get a vaccine, you don't want to know when it's coming in, right? So that's kind of what happened. Just a little distraction over there. So let's say, assume that I know this limit of one sequence. And I'm not even going to put the n goes to infinity. I'm just, the limit is equal to a, some number a. So that means that sequence, if there's the number a, it settles down on a. That's all that means. Get rid of that picture. And let's say I have another sequence, limit of b sub n is b. That means that approaches the value b as I move out that way. Then the limit of their sum is the sum of the limits. If I know that this goes somewhere and this goes somewhere, I can just add those results together. I'll give you some solid examples. I also know that the limit of a sub n minus b sub n is a minus b. I know that the limit of a sub n times b sub n, the product of those two, is equal to a times b. And I know, you probably see this one coming. If what? What do I have to make sure I don't do here?
Equals 0.
Yeah, we don't beat equal 0. Yeah. If b is not 0. Provided that, then all is good. And then one last one, limit of a constant, let's say k times a sub n, is just k times the limit. So let me show you what I mean. How would I use this? So example, suppose I'm just actually laughing at myself because I was about to explain that that was the abbreviation for suppose and that I was trying to save time, and now I just took 10 times the amount of time. So that's what I was laughing about. Suppose that the limit of some sequence is 3 and the limit of some other sequence is -1, then the limit of their product, you know what the terms are, is just -3. Limit of their sum is what? 2, thank you. Beautiful. Now let's just do one more here. Limit of b sub n over a sub n is -1/3. Beautiful. That makes life easy. It also means that when I'm looking at a formula and I have some formula, I can kind of take each piece of it in turn and break the analysis down that way. So for example, if I had the limit as n goes to infinity of, so what was that weird thing we just had? What was that weird ass fraction we had? Can somebody, what was that, the thing that went to through, bless you? What was it was like 3 plus 4n, was that right?
Mm-hmm.
Okay, and then what was on the bottom?
That's 2 plus 4.
2 plus 4, thank you.
And
3 plus n on the bottom, okay, cool. So if I had this plus this minus 2. So if I asked you, does that limit exist and what is it? You could go through here and you see, we already did this piece. And we know that this went to 4. So I could go and go, okay, well that goes to 4. Where's this one go? 0, yes, I heard a 0 whispered on the wind. 0. So remember this game, we've done this a lot. I've got something fixed over something getting bigger. Right, that's one of the big stories in this class. When that happens, you're going to 0. You got fixed over something blowing up, fixed over something going up, 0. Where's that going? Is that going anywhere, right? It's -2 and it ain't moving. So it's -2. So the answer here is +2, because I can just add up those limits and do each little piece separately. Makes life easy. You can break it down into little pieces. Let's look at a counterexample. So, what about limit as n goes to infinity of -1 to the n? So we plot it. Here's 1. It only spits out 2 things, right? 1 and -1. When n equals 1, we're at -1. Then we go to 1, and then we do this, this, this. Is that settling down? No. Limit does not exist for this. It does not settle down. So this limit does not exist. Doesn't settle down. It's a great one to know. Really great one to know. Let's look at another one. What about limit as n goes to infinity of n factorial? So we look at the sequence. So n factorial, when n equals 1, we got 1. When n equals 2, we're 2. N equals 3, we're 6. Then times 24, 120, 720. Oh, good Lord. What's that, Cassie? Yeah, I like that.
It doesn't slow down.
It doesn't slow down. It's freaking blowing up, right? So this does not exist either. We could say there's technical ways you could not exist. We could say it equals infinity if we wanted, and that's okay. It's an infinite limit. What is this limit? Limit is n goes to infinity of 7 over n factorial. Yeah, what's that? 0, right? Fixed thing, blowing up bigger than most stuff we've ever seen. So this goes to 0. Does that make sense to everyone? So you can't use L'Hopital's rule on this because this function is not differentiable. This function is weird. You can't L'Hopital a factorial, so that one you have to like figure out what to do, just kind of intuitively. Let's look at one more. And I'm going to help with this one. Okay, so the top isn't quite fixed, right? It's bouncing, 1, minus 1, 1, minus 1. Bottom's blowing up. What's your suspicion here? What do you think is long term? So like pick a really big n. N is 1,000. Let's look at it. So when n equals 1,000, what's our output? So when n equals 1,001, 1,001, what's my output? What's the sequence value? This is a sub n. Wait, what? I thought I heard something.
1 or -1.
Yeah, -1 over what?
1,000.
1,000, there, yeah, good, you know what's going on, it's all good. What about when n equals 1,001? 1 over 1,001. Where does it seem like we're headed? Seems like it's getting smaller in magnitude, right? It's hard to say because this one's negative and this one's positive, but the general feel is that they're shrinking. And if we actually plotted the sequence out, it would look like this. So if we got our little plotting tool out, we could see that this limit is 0 with that plotting tool. But let me show you a way to think about this without a plotting tool. So the plotting tool, like seriously, like the intuition you will gain from that is immeasurable. And it's really indispensable if I'm going to use another in word that starts with in. So here's a really helpful theorem. We have this thing called the squeeze theorem, or the sandwich theorem sometimes. And sadly, that did make my stomach growl. I'm so freaking hungry. So it's limits. So suppose we have 3 sequences. We have an A sub n, a B sub n, and a C sub n. And I'm going to draw a picture for this. It's going to really, I think, make this very clear. First, let me label some things. And A sub n goes to L, C sub n goes to L. Let me just write the whole thing out first. If A sub n is below B sub n, which is below C sub n, for n greater than or equal to some cutoff. So like eventually. What this means is eventually and forever. Forevermore. So romantic. So if this happens, then this middle sequence gets squeezed to L. Then B sub n must go to L as well. And so here's the picture. Here's L right here. And I'm saying that A sub n is underneath B sub n and C sub n is on the top. So here's C sub n. Let's say it's doing this. So this is the C sub n up here. And then the A sub n's down here. A sub n's underneath, and then I probably should use a different color for the B sub n. The B sub n always lives between these two after some cutoff. So after some point, let's say right here, here's my cutoff. So like this event could be like crazy out here. It doesn't have to necessarily be related, but eventually at some point, I know that it lives between these two. Then they squeeze it to the same limit. So it's kind of, with the picture, it makes sense, right? That this one's going to L, this one's going to L, and the other one lives between it, and so crushes it. Oh shit, hold on. So, let me get my friend back up here. So I had this sequence. I can prove it goes to 0 using the squeeze theorem, and here's how. So to really understand this will be the last thing we do today. And then Austin will have an amazing story on Friday. Do not fucking miss that. Like, seriously. The top is always kind of fixed at n. What's the most the top can be? No, so it's like the output, so like -1 to some power. What's the most that could be? What is -1? What does this sequence do? -1, +1, -1, positive. So 1. So the most it can be is 1. What's the least it can be? Awesome. Now I got something fixed over something blowing up on both sides. Where does this go as n goes to infinity? 0. Where does this go as n goes to infinity? 0. Beautiful. By the squeeze theorem, the one in the middle gets crushed to 0 as well. So by squeeze theorem, -1 to the n plus 1 over n also goes to 0. So it's a reasoning tool. It's like an argumentative tool. If you wanted to do something besides look at the graph, I don't know, look at the graph, you know? Like you could actually communicate to someone, this is why that is certain to go that way. Ooh, wait, I got 5 minutes. I want to show you one last one. So speaking of squeeze theorems, let me just come back to full circle. Some full circle shit here that I didn't see coming, but I love it when this happens. Sometimes I think like my head is working ahead sometimes, you know, and then I catch up with it. Oh, that's a good point, Ed. So sine of n over n squared. Let's look at that sequence, figure out what it does. What's the most sine can be? The output of sine? What does sine live between?
1 and -1.
Absolutely. So it doesn't matter how weird this thing is on top. It's always less than 1. What's sine always greater than? -1. Good old squeeze theorem. Where's this go? 0. 1 over blowing up even faster than that stuff. Where's this go?
0.
0. So where does this thing go?
0.
Yay! Thank you, squeeze theorem. So we can argue some crazy stuff, beautiful stuff that way. That's it. See you on Friday. So yeah, there's a web work. Maybe take a few moments between now and Friday to look at the web work, get warmed up on it, ask questions. It'd be great. Thank you, sir. Yeah. Oh, yeah.